Welcome, everybody. Looking forward to the session today. So first off, who here has heard of OAuth? Oh, good. OK. So I am going to go over some of the background of OAuth, which maybe you are not as familiar with, and then talk about how OAuth is used today and also kind of what is being worked on in the future, where things are headed. So should be a lot of fun. I do a lot of things related to OAuth. I have a book, I have video courses. You may have seen some of my videos on YouTube. I also actually work on the specs at the IETF, working on a number of them right now. There's always a lot of interesting new work going on. So, OK, let's go back in time a little bit. And not that fast. You might be familiar with OAuth from buttons like these, like sign in with Facebook or whatever it is. Is this really OAuth? Yes and no. It's not. It's technically, these are built on OAuth, but these were not the original goal of what OAuth was set out to solve. The original thing that OAuth was created for was to stop this kind of thing from being common. This used to be very, very normal on the internet. You would go to a random website and it would be like, hey, let's log in with your Gmail account. And then it would ask you for your actual Gmail address and your password to your Gmail account. And in case you weren't sure about which password it was asking for, it says your email password, really. So hopefully at this point, you don't go around giving your email password to random websites. I think we're generally pretty used to this concept by now. But just to be very explicit about it, why is this pattern bad? What these websites are usually intending to do is to access some part of your data that's in your email account. In many cases, it was the contact list. It was find your friends. So it only needs access to some of the data in your account. But as soon as you give it your password, you're giving it access to everything in your account, including the ability to change your password. So the other important thing, though, is that even if you intended to give the app all of the access to your account, there's no way to take it back. There's no way to undo that. So once you've given it your password, that is the key to your account. So essentially what this means is that by entering passwords directly into apps, you are trusting that application completely. So ideally, there would be a solution for apps like Yelp to access data in your account that you want to share, because people do want to share data in their accounts for various reasons, like finding their friends. So ideally, there would be some way to access some part of the account while preventing access to other parts of the account. And this accessing data part is really what OAuth was originally created for. How do we let apps access data without sharing passwords? It's actually very similar to checking into a hotel, where you go to the front desk and you check in, you show them your ID and a credit card, and then you get back a hotel key. That key represents your access to things in the hotel. It doesn't represent you as a person. It's not an alternative ID. It doesn't even usually have any identifying information on it. It represents that you can access resources in the hotel. So you take that key and you go to the door and you swipe it and the door opens up, because the door knows that that key is authorized to open it at this point in time. And that access may change later. It might give you access to multiple doors in the hotel, but it's going to be some sort of limited access, which is very different than, for example, you go to a hotel and they give you the skeleton key that can open every door, and they just kind of hope that you only open the doors you're allowed to, right? So, OK, so back in an OAuth flow, you're probably familiar with this pattern where you're on a website and it's asking you to sign in or grant access. It's going to send you away from that website to the actual account, in this case, sign in with Google. That's where you log in. You enter your email address, you enter your password, you enter your second factor of some sort, and then usually you get asked for if it's OK, if you actually want to grant this access. And then once you have finally gone through all this, you get sent back to the website and you are logged in, or it's able to access the data. So again, accessing data is what OAuth was really created for. I want to go over a quick version of what the different actual roles involved in an OAuth flow and how the data kind of moves around. So in an OAuth flow, we're going to talk about users, usually, who are using some sort of, they have a browser or a mobile app, a mobile phone. That browser is accessing a website, or the mobile phone is running an app, and that application wants to access data in some API, in OAuth terms called resource server. In order to get access to that API, it needs to actually go through this OAuth flow to get an access token it can use. So the client is going to first tell the browser or the user agent to go send the user over to the OAuth server. That's where they're going to log in and do whatever authentication steps and consent steps are necessary. And eventually, it's going to send back to the client. The authorization server is going to redirect back with this temporary code. It's an authorization code. The client will then exchange that code back at the authorization server for the actual access token, like a key. And it can use that access token to go make API requests. The API obviously needs to know how to validate tokens, so it can happen in a number of different ways. We'll get into some of the details of that later, but one way it can validate tokens is to go and ask the authorization server if the token is valid and get a response, and eventually returning data. So this picture, we're going to come back to this picture again when I start talking about some of the other extensions to OAuth, because a lot of the extensions target different parts of the flow for different reasons. An alternative way to look at this is this kind of like sequence diagram. So we'll go through this again really quick in this different format. Kind of helps to visualize it differently, I think. So again, the user agent is going to, where the user clicks log in the browser or in the app, that application is then going to tell the browser to go visit the authorization server. And you might notice that I have this kind of loop arrow here because the application at this stage is not actually making a request over to the OAuth server. It's telling the browser to go there. So it's actually a redirect. So then the user's browser lands at the OAuth server, they log in, they do the consent step, and the authorization server wants to give this temporary code back to the app, but it doesn't have a way to give it to the app. It actually sends it to the browser first, and the browser takes it to the app. And this is a really important step. It's a really important aspect of OAuth, this redirect concept. Then that application can go directly and talk to the OAuth server and exchange that code for an access token. So the colored lines here, it turns out, are significant, and the animation wasn't supposed to carry over to that slide. So the top half, the blue part, is all happening in the front channel. Front channel essentially meaning that it's all happening through redirects. The two things that are talking to each other here, if you look at who's trying to actually send data, it's the app is trying to talk to the OAuth server, and the OAuth server is trying to get data back to the app. But they don't talk directly to each other. They always talk through the browser, through redirects. That's the front channel. The back channel is kind of like the normal HTTP request. They can talk directly to each other. This is also this is something that's, it's not necessarily unique to OAuth, but it is kind of core to OAuth, and it's a source of a lot of the things that we have to do to secure the use of the flows. So the back channel is kind of like the normal way to make requests on the internet. A HTTP client talking to an HTTP server, hopefully over HTTPS, but it essentially means that that connection is direct. There's encryption in that connection, and we know that the response was received without being manipulated, and that's all great. Anytime we're using the front channel, the two things talking to each other have to go through this sort of untrusted third party, the browser. So there's a lot of opportunities for things to go wrong there. The user can change the data that's being sent between the two parties. Browser extensions can manipulate the data. They can read the data. So there's a lot of different things we have to do in order to protect the use of the front channel. So, okay, OAuth sets out this framework for getting these access tokens to apps. It's described in two parts at the beginning, OAuth 67, or RFC 6749, OAuth Core, and 6750, which is bearer tokens. There's not very interesting reasons for those documents being split. It's not super relevant anymore. They're kind of all just talked about as one thing at this point. The core spec talks about a number of different ways that apps can get access tokens. We looked at the authorization code flow just now. There are a few other versions of that. The implicit flow is a shortcut. The password grant is there's no redirects happening. It's just a kind of direct authentication from the user. And then the bearer token spec defines a couple different ways apps can use access tokens. Because of the problems of this using redirects in these different kinds of applications, there's a number of opportunities for things to go wrong. So we need to start adding more layers of security to kind of fix things up. The first one of those is called PKCE. It's actually published as a separate RFC several years after originally OAuth was created. And this, we'll talk a little bit about it later, but essentially it's protecting the use of the front channel. And then there's another RFC that talks about how we should be using PKCE in mobile apps. Then later, it turns out that PKCE solves attacks that were also possible for not mobile apps, regular web server apps. So now we have this security BCP that comes along and says, actually, don't use the implicit flow anymore. It's pointless. We need PKCE everywhere. We probably shouldn't be sending access tokens in query strings anymore. And at this point, you're probably thinking, doesn't make any sense. Like, I'm just trying to just build this app. Like, I don't care about all this. And it's true. There's a lot of different specs involved in the OAuth process. It's partly because of just the slow evolution of understanding of the security space. It's partly because some of these features are required by some business needs where others don't need those features, so they get kind of broken out into different specs so that you can kind of pick and choose what you want. But it's kind of hard to navigate. And at least some of this is considered core OAuth, or like when we say OAuth today, what we actually mean is this kind of baseline, which we're now consolidating into what actually is a much simpler picture of use authorization code flow with PKCE all the time. There's also the client credentials grant for when there's no user involved. And then a couple different ways to use tokens. But that is what we're that's what we're working on right now with updating OAuth 2 to OAuth 2.1. OAuth 2.1 is this evolution of what is now almost 14 years of OAuth 2, where it kind of got a bit messy. I'm trying to bring it back together and say, like, okay, this is what we mean now when we say OAuth today. So it's not a whole new thing. It's actually just like the best parts of OAuth 2. We're taking out a lot of the parts that aren't needed anymore, a lot of the optionality that was there for reasons that aren't relevant anymore, and trying to just give it a name so that we can refer to it by something, so that we can consistently refer to it when we say what OAuth is. It's also an opportunity to add references to a lot of new extensions, because there's a lot of new interesting work going in that wasn't around when OAuth 2 was originally published. So at this point, I should also talk about how OpenID Connect relates to this, because OAuth is just one part of the picture. Think of OAuth as the hotel key example. OAuth issues access tokens. Access tokens are used to access data. That's why they're called access tokens. Hotel keys are used to access resources in the hotel. The hotel key does not say anything about you, a person. It is not a representation of your identity. It has nothing to do with any of that. So essentially, if we want to answer those kinds of questions in an OAuth-like flow, we need to add OpenID Connect. So OAuth is all about accessing APIs, whereas OpenID Connect is about identifying the user. So think of OAuth as the way that an application can go make API requests. It's going to use an OAuth flow, get an access token, make API requests. The OpenID Connect extensions to it are going to actually tell that app about the user who's authenticating. So the way that it's going to do this is OAuth is going to issue access tokens. OpenID Connect is going to issue ID tokens. So you can think of access tokens like a key. You can do things with a key. You can use it. You can go around to different resources and open different doors. An ID token is more just like a statement. It's just like a statement about something that happened. And there's going to be a bunch of information on that. It's going to be like this user logged in at this time to this application from this place, whatever else you want to add into that It's like a receipt. It's just a statement about things. And importantly, it can be validated. It has a signature, so you know that it's a real statement issued by the OpenID server and not faked. But this also implies that the things that are going to be reading these two different tokens are different things. An access token will only ever be read by an API that it's going to be accessing, whereas an ID token is read by the app. And this goes both ways. So this means if you're building an API, you should never expect to see ID tokens, because ID tokens are not part of that ecosystem. They're part of the application went and got both tokens, and then as an API, you're going to see the access token. If you're building the application, and you are going to get both of these tokens, because you need one to go and make API requests, and you need the other to learn about the user, you're never going to read the access token. The access token should be treated as just a random string of gibberish that has no significance to the app. It's only the API that cares about that. So I want to go back to this idea of front channel and back channel again. So the back channel is the server-to-server connection or client-to-server connection where it's HTTP requests actually sending and receiving data. And the front channel being passing data between two pieces of software through some other software, a browser. So with the back channel, it's almost like we forget why it's so useful because it's just kind of assumed that the default. When the client makes a request, if we're using HTTPS, it's going to do certificate validation, so we know we're talking to the right server. That also establishes an encrypted connection, so you know that that data can't be tampered with, and that means that you know that when you get a response from an HTTP request, you know that it's the data you were expecting. I like to think of it as hand delivering a message. Like you walk up to somebody, you can take a thing, you give it to them, you can see they took it, they know who you are, you know that the transaction was successful, and you know that nobody else came in and stole that. The front channel, however, is more like taking whatever message you're going to send, putting it in an envelope, sending it in the mail, and then hoping that it gets there. And this is really important to remember on both sides of a transaction. If you send data in the front channel, you have no way to know if it was received. Just like when you send a letter. You send a letter, you have no confirmation that it was received. Even if there was a tracking number on the letter, all that means is that the delivery company says it was received. It's not actually proof, right? And on the receiving end, you have no guarantee of where this actually came from. Was it from the OAuth server? Was it from somebody who just put a different return address on the envelope? Did they open it up, take out the contents, replace it, and seal it back up? You have no way to know, right? So essentially, anytime we're using the front channel, from either side of this transaction, you have to just remain skeptical. So why do we use it at all then? Well, this is actually how we let the user get involved in the flow. Without the front channel, we would have users directly entering passwords into apps, which open up a separate set of problems. This is also how we're able to add two-factor auth into the OAuth flow securely. So I want to give you some concrete examples of front channel and back channel because it can be kind of confusing once you start looking at different actual deployment scenarios. It's kind of the most clear in a server-side app. So this is like any kind of language that's running on a server somewhere that the user is accessing from a browser. This is the most straightforward separation of the two, where the separation is the most easily visible. So if you think about it from the authorization server's point of view, it's getting a message in the front channel first, and it's getting a message in the back channel second in the OAuth flow. So the front channel message is coming from the user's browser, which means it's going to have a user agent string, it's going to have an IP address that's going to be their home internet, whereas the back channel message it's coming from the web server that's running this application. So it's going to be running in AWS or something, like some sort of totally different IP address where the two requests are coming from. And then that kind of makes it very clear why, from the authorization server's point of view, why there's no immediate connection between the two requests. They're coming from two totally separate places at different times. The same concept is also true in single-page apps and mobile apps, but it gets a little bit more blurry to see the differences. In a single-page app where you have JavaScript code running in the browser, the front channel is when the JavaScript code tells the browser to redirect somewhere, right? Where it's actually telling the browser to go make a request. The back channel is when the JavaScript code itself makes an HTTP request using fetch or XML HTTP request or AJAX or whatever. So even though from the authorization server's point of view, the request is coming from the same IP address, because both of these are in the same device, we still have to consider them separately, because there's still a lot of the same opportunities to kind of inject or mess with the requests. In a mobile app, it's similar, and the lines are a little bit even more blurry now because in mobile, we have the front channel is the use of these system APIs. On iOS, it's called AS Web Authentication Session, but essentially it's that little browser that you'll see that'll slide up inside the app, and the app no longer has control over that browser. So it can tell the phone to go to a certain address, and then it kind of doesn't see anything that happens until eventually a callback handler is called in the native code. Whereas a backchannel request is the native code actually using an HTTP client. So if you haven't caught on, the theme here is backchannel is an HTTP client, whereas the front channel is not an HTTP client. It's the code that you're writing, not making an HTTP request. It's telling the browser to do something. So let's talk about some of the recent OAuth extensions that have been published, and I want to kind of relate them back to the original diagram and also the front channel versus back channel. So the first one I want to talk about is called pushed authorization requests. It's RFC 9126, so several thousand RFCs later. If we think about back to this diagram, the first thing that the app did in the traditional OAuth flow was redirect the user's browser. So it first tells the user agent to go redirect to the OAuth server. That's a front channel request. The problem with a front channel request is that the authorization server is getting that request not from the client. It's getting it from the browser. So as a user, if you happen to see the query string that is, the app is building, you can modify it. And you can add scopes that it's requesting or delete scopes that it's requesting. And you can cause all sorts of chaos with applications by doing this. So pushed authorization requests changes the way the flow starts to actually starting the flow in the back channel. So instead of redirecting with all these things in the query string, the client is actually first going to make a back channel request to the OAuth server. And this is good for both clients that have credentials and not. If the client has credentials because it's a server-side app, now that first request can actually be authenticated, and that means that the OAuth server can really know for sure that it's that app making the request. For JavaScript clients or mobile clients, there's no authentication in the request, but it's still better than the front channel because at least the user doesn't have the opportunity to mess with the query string parameters, and anything else that can see query parameters in the request it's all hidden. It's also possible to send much larger requests this way, which is important once you start getting into things like banking use cases where you might have really large initial requests because you're trying to describe a request of authorizing access to a bunch of accounts or authorizing specific payment between different accounts. So it's just a lot nicer to kind of bundle those up into a post request. There's also rich authorization requests, which is it's actually one of the good reasons to use pushed authorization requests, because what this does is affect you could use it in the front channel or the back channel, but it makes more sense to use it with push authorization requests. Essentially what this is an expansion of the idea of OAuth scopes. So with OAuth scopes, you would be typically saying, this application is trying to get access to this user's email or contacts. And that's pretty rough. It's like coarse-grained, right? So if you wanted to be able to describe more specific things, like this app is requesting access to this particular account or wants to authorize the ability to pay up to $10 to these 10 people. None of that is really going to be possible with scopes without going pretty overboard with defining scope strings. So essentially, it's a syntax it's a framework for describing those kinds of syntaxes. Again, it has a lot of uses in the banking space, as you can probably imagine. Another one that was recently finished was is the step-up authentication challenge. So this one affects the link between the client talking to the resource over the API. So the client talks to the API, it's making API requests, and at some point, that API might say, it's been too long since you've last authenticated. You last logged in at the OAuth server a week ago, and you've been kind of riding on access tokens and refresh tokens since then. So step-up auth is gives the ability for the API to tell the client that the user needs to re-authenticate or do a second factor. So if you imagine from the API's point of view, you're going to get this access token, and it's going to have information in it like when the user last logged in, whether they used the second factor, when they did log in, and at some point you might be like, okay, well, it's been too long. Like I need to know that the user is actually still there, because the app can go a long time using refresh tokens to kind of extend its own access without ever bothering the user. So that's a good framework for that. Speaking of access tokens, there is actually no requirement in OAuth that access tokens have any particular format. And you do see this in practice, pretty big range of things. It usually tends to be the case that in kind of simpler, smaller deployments, maybe not smaller, but simpler structures, access tokens will just be a random string. Like if you look at a lot of consumer websites, it's usually things where there's just like a website or a system, then they just use random strings. But as soon as you start getting into deploying more complicated scenarios or kind of moving your authorization server out somewhere else to a different subsystem and then having a bunch of different APIs, then the random string pattern starts to add a lot of complication. So the job profile for access tokens describes an actual a syntax and claims that are used in a JSON Web Token that you can use as an access token. This is where things start to get a little bit messy, though, with app developers, because as soon as an app developer sees that it's a JOT, you can recognize it from the pattern, right? As soon as the app developer sees that it's a JOT, they're like, oh, that means I can parse it, right? But no, like, again, just like a hotel key card, if you're using it, you don't care what's on it. You just care that what you're sending it to, what you're using it at, does know how to read it. So again, apps are never going to parse tokens, even if it's technically possible, because you're breaking the security barriers here. This is also a good time to mention the difference between random string tokens or structured tokens like JSON Web Tokens. If you are using a structured token like a JSON Web Token, what it's doing, in addition to defining a common set of claims, it's actually giving that API the ability to validate the token without network traffic. So if you start spinning up a bunch of different API servers in a bunch of different places, they no longer have to kind of share access to a database to look up these random strings. So one common use of this is in deployments behind an API gateway. Because what you can do here is you can actually have an API gateway do your token validation. And this gateway is on the public internet. It's going to be getting all this traffic from a bunch of random things, like with valid tokens, expired tokens. Attackers are going to be trying to get in. You're getting requests with tokens that have been revoked because a user logged out or whatever it was, and also just junk requests. You don't want to have all of those requests have to do a database lookup before you even process the rest of the request, right? So you can do local validation at the gateway layer. Look at the JOT, decide was it signed correctly, is it expired, and then you can throw away a lot of the traffic right there. However, it's usually not actually the end of the story, because you're going to let that gateway doing local validation will let through valid tokens, but also tokens that would have been valid if they hadn't been revoked for other reasons. Because essentially, if you think about a JSON Web Token, the server is going to create it. It's going to say it's valid for 12 hours or whatever it is. And what happens if things changed between the time it was issued and 12 hours when it expires? Things can change. Like, it depends on what you have in that token, but it could be scopes that were granted. It could be, well, maybe the user was deleted and the token looks like it's still valid for another 12 hours, or any number of things, right? different parts of your internal systems may care more or less about those. So there isn't even a correct solution. Kind of going back to the opening talk, there's no right or wrong, absolute yes or no on, it's all like, you have to decide what's the right, what are the trade-offs you're going to make in terms of speed benefits versus flexibility or usability. So if you have like your different internal APIs, maybe you have a customer API that's going to just return the user's current rewards points balance. Like that's not super sensitive information. It doesn't identify the user. It doesn't change very often. So if that API didn't go any further than just the local JOT validation, it's probably fine because like you're not going to leak that much information if you accidentally responded when the user account was deleted or if the user had revoked that app. But a billing API that's going to go charge the user's credit card, very different story, right? Like you want to make sure that at that moment you know for sure that that token is actually valid through all the other validation steps you're going to be doing. So for those, you can go back and do the token introspection or database lookup of some sort, actually checking your revocation lists, go back to the OAuth server and reject the revoked tokens. So one way to think about this is that access tokens, when they're a JOT access token, it's actually a cache of the state of the system when the token was created. And that cache has a cache lifetime, which is your access token lifetime. So you can change how the system behaves by changing your cache lifetime, and that has performance and security implications on both sides. So I just find it a useful way to think of it instead of trying to be more black and white about it, about this way is always right or this way is always wrong. So, okay, let's move on to some of the specifications that are getting close to being final. One of them is OAuth for browser-based application. It's actually called a best current practice. It is not defining new OAuth concepts, but it is describing concerns that are related to building OAuth applications in browser-based apps, JavaScript apps. The main thing this does is it lays out three common patterns for that you can usually use when creating a single-page app. That's going to be a pure single-page app or a backend for the single-page app, and there's two variations of the backend. One is where it's proxying all requests, and one where it's only kind of proxying tokens. So it's laying out these patterns and then describing what are the benefits and drawbacks of each pattern. And it turns out there's problems on all of them because browsers are just a very messy world to live in. So in a single-page app, you have no backend, right? The JavaScript code that you're writing is making API requests directly. So it needs to obtain the tokens itself, and it needs to use those tokens to make API requests. This is, it's not right or wrong, it's just this is a pattern, and there are trade-offs in the pattern. The main kind of concern here is the fact that the unique thing about this flow is that the browser is actually making API requests, so the browser has to have the token, which means it needs to store the token somewhere, so you're also dealing with token storage concerns. Don't have time to go into all of the concerns here, but do read the document if you're curious. But I want to point out the main differences between the patterns. The sort of middle ground pattern is where you end up with this backend that is only responsible for obtaining tokens and then sending the tokens to the JavaScript code. So so the JavaScript code still actually has the tokens and does make API requests directly to the resource server, but it's not responsible for that kind of initial obtaining the tokens. So your backend, for example, can be a confidential client, which means that only that backend can actually obtain tokens, and there's no way to impersonate it, which is good. So this actually does solve a number of issues that are attacks that are possible in a pure single-page app, but still leaves some concerns open because the JavaScript code does ultimately end up with the token. The third pattern, most common pattern, is the full backend pattern where the browser doesn't see any part of the OAuth flow, or your JavaScript code doesn't see any part of the OAuth flow. It's all handled through the backend, and the browser doesn't even make API requests to the APIs themselves. It proxies all the requests through its backend. And this is the most secure of the three. There are still attacks that are possible, but essentially what it does is it means that if cross-site scripting attacks happen, the cross-site scripting attacker can't steal any access tokens because the access tokens weren't even in the browser in the first place. The worst that happens is that the attacker can tell the backend to make API requests impersonating the app, which is about the best that you can do in JavaScript. So it's worth reading this full spec if you are finding yourself building any JavaScript applications, because there's a lot more to it than you might think, and there's a lot of really subtle tricks that can get you. And you may want to consider one of these patterns over others based on all those different trade-offs. Another largely, well, I don't want to say unsolved, but only recently possible to be solved problem is this problem of sender-constrained access tokens. So again, back to the hotel key example. If you have a hotel key and you go to the door and swipe it, it opens up, great. What happens if you give your key to somebody else? They can access the door just as well as you can, right? The key represents the authorization. So this is also true with OAuth access tokens. The access token represents the authorization. So if you steal an access token, you can use it just as well as the real app, because that is what is authorizing the request, which is, as you can imagine, not super great if you have a way to steal access tokens. And this is not a theoretical problem. There are, at this point, many examples, some of which are relatively high profile, where accounts get taken over through this kind of attack. This is an example of the Linus Tech Tips YouTube channel getting taken over and rebranded and then broadcasting cryptocurrency schemes because of this bearer token problem. If you can steal all the cookies out of the browser, you can put them into a new browser and they look just the same as the original browser. And it's all, the cookies and access tokens have the same problem. The problem is that the thing that was issued is the same thing that is used in the request. So if you can steal it in some part of the flow, either when it was sent or if it was stored on disk, you can impersonate that application. So the idea of sender-constrained access tokens is to require some sort of authentication of the software that's using the token or the cookie. And there are a number of different ways you can accomplish this, some of which are easier to deploy than others. There have been many attempts at this over the years. Many failed attempts, some semi-successful attempts. At this point, the ones that are relevant are the three at the top. Mutual TLS, it's not a new RFC, but it is kind of one of the harder ones to deploy because it's using client certificates in your HTTP client, which is awkward for a lot of HTTP clients, but also kind of awkward on the server side because you have to terminate it at the TLS terminator. So if you're using a gateway and a bunch of stuff downstream, it's like, it just doesn't really, it's hard to deploy in a lot of cases. Depop is a more recent RFC, which was created essentially in direct response to trying to find an alternative to mutual TLS. And it moves all that client certificate stuff into the application layer so that it's just an HTTP header that you can set, which means it can also be sent downstream through other layers of your server side. It is much easier to write code for. You can do pure JavaScript implementations of it in a browser. It's actually pretty reasonable to deploy. Signed HTTP requests is not an OAuth RFC, it's actually an HTTP RFC, and it's a general purpose signing method rather than for access token binding, but you could use it for access token binding. So Depop is kind of the purpose-built OAuth specific token binding RFC of choice at this point. I'm still optimistic about HTTP signatures personally, but there's no current work being done in the OAuth world to apply it there yet. I mentioned cookies. Cookies also have the same problem. They're bearer tokens as well. There are efforts going on by the browsers to actually solve that at the browser layer as well. So I think the one that is kind of coming out on top is Google's, at this point, device-bound session credentials. It's in Chrome right now behind a flag if you turn it on, and you can kind of prototype it. But essentially, it's the same concept of the browser has a key, and it is able to sign requests when it makes requests that the server can validate, so that stolen cookies aren't possible to be used anymore. So we are coming up on the end of the session. A couple of really quick things to point out that are kind of more of the future, even farther out work, just to kind of get your interest. If you are interested in helping develop any of these are all like open work items in a lot of the working groups that are just out there if you want to join. This whole idea of wallets weirdly has a lot of overlap with OAuth because it's again a similar thing of like you're getting a credential from somewhere and then using it somewhere. So there's a lot of similarities with OAuth flows, but some pretty different fundamental concepts as well. That work is kind of split in a few different places, but really interesting stuff. Another big problem is the client attestation problem. So usually we talk about this in the context of mobile apps. If you download a mobile app, you can't ship a credential into it. So how do you know when your mobile app makes an API request or talking to the OAuth server, how do you know it's really your app? It could be anybody. So client attestation is the idea of, let's figure out a way for that mobile app to do something that can prove that it really is your app and not somebody impersonating your app. There's a lot of interesting uses of token chaining. So if we look into an API, it's often made up of a lot of other smaller subsystems, and those often need to do something more than just passing the same access token along to every layer of this chain. So there's a lot of interesting options available for token exchanges or chaining or modifying tokens to be able to request things from downstream apps without having that same bearer token be sent along the whole way through. There's some interesting cross-domain use cases of you need to get a credential from one server but then use it somewhere else. So the sort of typical patterns that we would see don't apply. And there's 2 drafts right now that are in progress in the OAuth group for this. There's also some interesting revocation use cases of especially once you get into anything beyond just like the typical app to its own OAuth server, but if that OAuth server actually has you log in with enterprise identity providers, how do you handle the case of that enterprise IDP wanting to deactivate users across every app in the enterprise, right? Speaking of enterprises, there's a lot of work to be done here. The OpenID is a common use in enterprise for enterprise SSO, also SAML. But if you look at what actually happens in an enterprise deployment of things, you end up with an enterprise IDP actually integrating with a bunch of different applications. And then it kind of turns into a mess of all these tokens flying around, all these different devices, users logging in on 3 or 4 devices to the same applications. And what does it actually look like from the perspective of the app developers who are building these apps that get enterprise deals, needing to actually make sure that they provide the right controls to the enterprise IDPs. So there's a lot of work there to handle all the different parts of the flow. So one of the things that I've been working on most recently is trying to consolidate these use cases into a single place where you can actually go learn about how to make your app ready for enterprise customers, handling before and during and after authentication. A lot of what we talk about in OAuth and OpenID Connect is really just the sort of middle part of like the user logged in, but how did they get the account set up in that SaaS app before? How does that app know what the user is allowed to do within that app, all the entitlements part of it? What about after they log in? Just because they logged in once doesn't mean they should always have access from then going forward, right? So we need to handle things like what happens if a user's device is lost? They should get logged out of apps on that device. What about when the user is leaves the company. They need to get deprovisioned from the application. So there's a lot of those kinds of concerns that go far beyond just the OpenID Connect part of it. And even just last week, we have started a new working group in the OpenID Foundation called IPSI. The long name is Interoperability Profile for Secure Identity in the Enterprise, but essentially it's a collection of all of these different specs that are used in enterprise deployments, OpenID Connect being only one of them. And I'm really excited to get to work on this. It's a lot of interesting problems to solve. And if you are building SaaS apps and you have enterprise customers, you probably do care about this. So feel free to go to the website to learn more and join me in working on that. You can find this and a lot more information on auth.net. I keep it up to date with extensions and libraries and things like that, events that are relevant to the community as well. So feel free to check it out there. And thank you all very much.